Good afternoon and welcome to the Global Congress on Process Safety. This is a virtual Congress and I need a virtual haircut, but that technology is not available. We're looking at two full capacity generators. And the question is, why is the Calculated Emergency Power System, PFD, probability of failure on demand so high? Here's our content. We need emergency power to protect during a power loss. We have some LOPA scenarios with power outage leading to human harm, equipment damage, and environmental damage. We have candidate protection layers that may include pumps, compressors, and blowers that operate during the power outage. And of course, we need emergency lighting. To put this in LOPA terms, the initiating event, i.e. or initiating cause, is the power outage. The consequences are human harm, equipment damage, and environmental damage. Here are candidate IPLs. The bottom line is that we need power to support the IPLs. No power, no IPLs. Here's the schematic of the EPS. The generators are diesel driven. We have a bulk fuel tank with two different transfer pumps powered by the same UPS circuit to transfer the fuel to the A fuel tank and the B fuel tank. Each genset has a dedicated fuel pump, two starters, and two batteries. And then each genset has circuit breakers as shown, and generator A has a transfer switch. And if normal power is not available, the transfer switch puts generator A output into load A. That's part of the load. Generator B likewise has a transfer switch. If normal power is not available, puts its output into load B. Both generators can handle the total load A plus B, and for that to operate, the tiebreaker circuit breaker must close so that one generator can feed both loads. When we test this system, we run the generators weekly. We have a quarterly inspection and maintenance. We have a full functional test every 4 years. So what do you think? Are the two generator systems completely independent? And the answer is a resounding no, because we've already seen the common bulk fuel system and the common power to both fuel transfer pumps using the same UPS circuit. By the way, UPS stands for Uninterruptible Power System. But there are a number of faults that can prevent any UPS from providing power. We also have common causes from the genset parts from the same manufacturers, maintained by the same technicians, and operated in the same environment. We have safety circuits in the relay cabinet that can trip both gensets. Because we have a lack of genset independence, we are unable to use a generic PFD value from industry data. It's necessary to do a fault tree analysis for the EPS to determine what its probability of failure on demand is. So here's the top event for the fault tree. EPS power needs to go to the users for a required length of time. The top event is an OR gate. If any of the problems from the three input gates below it occur, there is no power to the UPS for the required time. The generator power gate is an AND gate because if either generator runs, we should have enough power for the load. If the full load needs to go to one generator, then the tiebreaker is needed. Here are the subtrees for the generators themselves. These are OR gates, so anything that happens underneath will prevent the generator from providing power. The generator must start, and the electrical system must work for the generator. And we already know that the generator is going to go down once a quarter for 8 hours for the preventive maintenance. FR is the frequency rate for the preventive maintenance 4 times per year. Gen A and Gen B have similar subtrees. The results of the fault tree: if we have a 4-year proof test interval, the probability of failure on demand is 0.3. If we have a 1-year proof test interval, the probability of failure on demand is 0.1. That is, 1 time out of 10, the gensets cannot provide the needed power during the main power outage. This probability of failure on demand is similar to a SIL-1 safety instrumented function, or SIF. We have to add this probability of failure on demand to the probability of failure on demand for the IPLs. Surely a system with redundancy, weekly test runs, quarterly PM, and annual proof tests should give a lower probability of failure on demand. Why not? Well, the culprits are common cause, the weekly test run coverage, the quarterly PM coverage, the 4-year full functional test that we do at that frequency currently, the large number of relays in the control circuit, human error in adjusting set points for electrical safety, such as voltage, current, and spurious trips from the electrical safety devices. We'll look at each of these in turn. Common cause is one failure disables 2 or more seemingly redundant systems. For example, power from Gen A, power from Gen B are both disabled by the same problem. When genset parts come from the same manufacturers, and the same manufacturing flaw could trip both generators. They're maintained by the same technicians, and they're operated in the same environment. We've already identified the bulk fuel system as a common cause because of the single tank and the power from one UPS for the 2 transfer pumps. It turns out we have common causes farther down in the tree, CCF1, that can prevent both generators from starting. Likewise, we have common causes, CCF2, that can prevent both generators from producing the electrical power that's needed. An example of common cause for redundant equipment is, remember we had 2 starters and 2 batteries for each generator. So generator B has starter 1 and starter 2. If one doesn't work, the other one should be able to start the genset. However, because of common cause, their starter may be able to start the generator for the same reason. So we have generator B, common cause. The failure rate for the common cause, FR, is 10% of the failure rate for a single starter. We have a similar tree for the 2 batteries for each generator. Now we come to the coverage for the weekly, quarterly, and the 4-year test. Coverage is the fraction of failures that a given test can detect. In our weekly test, we can detect some failures, but if the diesel engine starts, we know simply that 1 out of 2 batteries and 1 out of 2 starters are working. We don't know the status of each battery or the status of each starter. Battery 1 could work, battery 2 could work, both batteries could work, likewise for the starters. For the quarterly PM with an oil change and some inspections, we are not able to detect very many hidden failures. In the 4-year full functional test, now we can detect many hidden failures, but it's 4 years before we can do it because none of the other tests have the coverage to find them. We have a large number of relays in the control circuits where there are opportunities for loose wires to cause spurious trips. We have human error in adjusting the set points for the electrical safety devices, voltage, current, and timers. This is old electromechanical equipment, difficult to adjust, had to hook a meter up to it, turn a screw, and it was error prone. We have spurious trips from the electrical safety devices. Spurious trips are safe failures from protective equipment that shut the equipment down when it was not supposed to shut down. So it's a fake trip, if you will, for electrical faults, bus failures, voltage failures, generator trips, engine failures, and it can trip one or both gensets. Recommendations to reduce probability of failure on demand came from examination of the fault tree. We need to reduce common cause failures wherever possible. We need to improve the weekly and monthly test coverage. We need to increase the frequency of the full functional test we recommended once per year. We need to replace the obsolete relay cabinet with a safety-rated PLC. We need to minimize the effect of safe failures of protective equipment. We need to reduce human errors by replacing the error-prone electromechanical timers with a safety-rated PLC. And we need to stagger maintenance and calibration between Gen A and Gen B, different crews or different days. This last feature is a very important one. PII has written papers on this, and you can refer to those for additional learning. And finally, we need to maintain the EPS integrity using a management system that takes care of the EPS throughout its whole life cycle. And what does that mean? It ensures the organization is committed to process safety, including a process safety culture, compliance with standards, process safety competency, and workforce involvement. It means who does what, when, what training is required, what are the competencies, and how are they demonstrated? How are we going to audit this to be sure everything is going to happen? How will we investigate deviations and make corrections? And finally, how will we manage change? In conclusion, the facility knew that the performance of the backup emergency generators was less than desirable. They were surprised that the fault tree analysis showed a relatively large number of device failures that could trip both generators. The fault tree analysis provided the basis for the recommendations, and we realized we needed a management system to ensure that the integrity of the EPS is managed throughout its life cycle. This is one example where we have to go beyond LOPA to more details because two redundant devices are not fully independent. Thank you for listening. I hope you have a good conference. And here is my contact information in case we don't get all the questions answered.